Hello everyone, thanks for coming to this tutorial. This is Yuxin Wu. I'm a research engineer at FAIR, and in this talk I will introduce Detectron2. You might have learned about detection and segmentation from the previous talk in this tutorial. If you haven't, I strongly recommend checking out those tutorials first. Detectron2 is the software library that implements those object detection and segmentation algorithms. And it is also a research platform for us to develop more algorithms on top of it. Today we will do some basic introduction of Detectron2, and then we will talk about a few interesting aspects of how it is used in our research and production. Since the original fast RCN was invented in 2015 and many other object detection models developed since then, there have been a lot of different code bases and projects that implement detection models. Here I'm showing a timeline of some popular projects on the left side of this arrow. These are projects that come from the same family where they all inherit some aspects of the preceding projects in terms of either code structure or design, and we have come a long way from the original code base into Detectron2 today. On the right side, there are a few other relatively independent projects that are also very good quality and also implement these detection models. Detectron2 differs from its predecessors in the following aspects. First, it's built with PyTorch, which offers greater flexibility for object detection research. It includes better and more advanced models, and they are all very carefully implemented to obtain the best accuracy. It is designed with more modularity in order to support users who use it as a library inside part of a larger project. It is also more efficient. It is able to train models much faster than the older generations of the library, and the models are also deployed on thousands of machines across Facebook, making predictions on Facebook scale data. With the evolution of object detection research and codebase, what we're able to do today is very different from where we were a couple of years ago. Object detection was once only about detecting bounding boxes on images. Today we can do much more on that. We're able to localize key points for every person in the image, or draw a 2D mapping of the body parts of a person. This is also called dense pose prediction. We were able to segment every object in the scene and draw a boundary of them, or even beyond objects, to label every pixel in the scene, including both the foreground and background. This is a task called panoptic segmentation. These are what object detection models are able to do today. Let's first take a look at the models. Here in blue boxes, we list the models that are implemented with Detectron2 by Facebook. Many of them are from the RCN family of models, and some others as well. We're also very happy to see more detection models implemented by the community using Detectron2. For example, some models we listed here in the green boxes comes from a great project developed by the University of Adelaide. In Facebook, we currently put a lot of focus on the RCN style models because they are quite versatile and can easily adapt to different tasks. Here we show a diagram of how a generalized RCN model makes predictions. An input image goes through a backbone feature extractor to extract image-level features. These features are then used to predict region proposals, which are regions that are likely to contain objects. Features are then cropped using these proposals to become region features. What makes this system very flexible is that we can predict a bunch of different instance-level attributes using these region-level features, such as bounding box or segmentation mask for every instance, or key points and dense pose for every person. We can also make image-level predictions using the image-level features, such as predicting a semantic segmentation mask. These predictions can be further combined into panoptic segmentation, which labels all the objects and background pixels in the image. These are only the common tasks that an RCN system is able to do. An RCN model can be easily extended with more prediction heads that use image-level or region-level features to make different types of predictions. How do we manage all these models? In fact, many of the models are not actually included inside Detectron2, but as extensions which use Detectron2 as a library dependency. One important goal when we build Detectron2 is to allow it to be used as a library. What this means is that we should allow users to add new things without having to touch Detectron2's code. That includes adding new datasets, new models, new evaluation metrics, or even new data modalities and new tasks. In fact, allowing users to add their new data modality is quite difficult, but they are very crucial in the new research we're doing, such as predicting 3D meshes or dense pose. As an example, in our Colab notebook tutorial, which you can find online, we show how to import Detectron2 and then add a new dataset to it. With less than 100 lines of code and a few minutes of training, we can obtain a model to detect and segment balloons. Balloon is, of course, only a tiny example, and a few larger research projects have also been developed in this way. Mesh RCN is one such project, and it predicts 3D structure of objects detected in the image. You will hear more details about this project in later tutorial about 3D understanding. This project is built on top of Detectron2, and it only includes the extra files that are special to this project, including code that defines its new dataset, its new data loader, and its own evaluation metrics. And of course, a few new heads in the RCN system. The reason why we emphasize this so much today is because in the research community, many research projects are not designed in this way, and that includes Detectron1, which is our predecessor. If we need to implement a new research model like Mesh RCN or Dense Pose RCN in Detectron1, we will kind of have to fork and modify a large part of it. Similarly, you might have also heard stories that back in the days when we used Caffe for deep learning, everyone had their own custom version of Caffe because they need to make changes there in order to do a new research. Seeing all those issues in the past about forks of a framework, avoiding forks is an important reason why we encourage using Detectron2 as a library. It gives us a more healthy community where users can share improvements from a common library instead of forking to everyone's own versions that easily becomes obsolete. It makes maintenance much easier because now every project is separate and they only have to care about themselves. With this approach, we're also able to easily split between internal and external code. This is because some production models that we use in Facebook are actually more complicated and highly customized for the specific application. These models are quite different from the standard models in academic settings that we would like to open source externally. Despite these benefits, we admit that doing research in this way is not always the easiest way, especially during the prototyping phase. Sometimes we just want to quickly try out some new research ideas, and that may involve changing a few lines of code here and there, and it's often easier to just go hacky and modify the code directly. Another issue is when being used as a library, we'll have to worry more about the stability of API that we provide. It's maybe easier for a little bit lower level libraries such as PyTorch itself, but it can be harder for a higher level library that provide research models. Also, sometimes Detectron2 just does not have the exact building blocks that are suitable for your own task. And this can happen in very new research because research is about doing things in new ways that haven't been done before. And the more groundbreaking a research idea is, the less likely there will be already a building block that's ready for it. And that's just the nature of research. We're trying many things to make Detectron2 more like a library, and I'll give a few examples here. One thing is about the so-called trainer, which is a pretty common concept, and it appears in many other projects as well, besides Detectron2. It's something that lets users define the necessary information needed for training, such as the model, the optimizer, etc., and it will do the training for you. This is pretty nice for the standard training settings, but once you want to do something more customized and more fancy, these libraries, including Detectron2, will tell you to write some callbacks or hooks, which are something you need to implement following certain predefined rules, and they can quickly become quite unintuitive. You can find such patterns in many high-level training frameworks. On the other hand, Many researchers like to write their own custom training loop because they like to have the control of the training in a more straightforward way, instead of leaving the control to a system that they're not so familiar with. Therefore, our approach is, despite of having a trainer for the standard settings, we also try to make sure that writing a custom training loop is equally easy, and we provide examples for both. On a higher level, what we're trying to do is to make each component work independently on their own. We want to make our model work just like any other PyTorch model in any other PyTorch libraries, without necessarily relying on a specific training system. Another example is about configurations. Configuration files or config objects are also very common in different frameworks. The way they're often used is that you basically follow some rules and provide certain keys and values at certain places, typically a config file, and then they will be read by the framework, and certain features in the framework will be enabled or disabled according to the config. So config is essentially a special part of the system that's used to control other parts of the system. That's why when we think about configs, we would usually link this concept with a larger system or framework rather than a library. In Detectron2, we also have a config system, and it lets users build the standard models with standard features easily, because in that case, all the nice defaults can be loaded from a config file that we provide. In the meantime, we also allow explicit construction by just passing in the explicit arguments. For example, to construct an RCN model here, we can just provide a backbone module, an RPN module, some of the heads, etc. And this, again, is trying to make sure the models can work well enough on their own, without necessarily depending on another part of the system. Building a model in this way would require some more expert knowledge from the users, but it also gives users more power to combine different building blocks with more freedom. And we will continue to allow both usage of our system. So these are some of the engineering directions we're taking in Detectron2 to continue to improve its usability as a library. Next, I will talk about a few aspects of computer vision research using Detectron2 as an example. We'll start with the model zoo that we published on our GitHub. It's a list of baseline models that we trained and released, and we'll discuss why we choose these models and how we use them in our research. This is a table from our model zoo that contains some of the mask RCN models that we provide. The first thing we notice is that we provide models with different backbones. From the earlier talks, you might have known that these are some standard CNN models that extract features from the input image, and in object detection, we often start with a general feature extraction backbone, such as a ResNet, and there are some changes that are specific to the mask RCN algorithm, such as feature pyramid network, and etc. When looking at these models in more details, we will find that those backbones equipped with the feature pyramid network, or FPN, they seem to always perform the best compared to other models. They're both faster and more accurate than the other backbones that we listed here, as you can see in the table. So you might wonder, why do we bother with these different types of models given one type that seems strictly better? Well, it's because research is not just about better numbers. Even if something currently appears suboptimal in some metrics that we define, it might still have the potential to become better in the future or in a slightly different evaluation criteria. For example, if you only care about detecting larger objects, it turns out that the models with the C4 type of backbone can become more competitive than it seems in this table. Also, object detection models are not just about object detection. In fact, the choice of backbone can play an important role in representation learning research, because object detection is a great way to evaluate how good a learned representation is. Imagine we have a standard CNN model that we pre-trained in some ways and want to evaluate whether the representation that we learned can transfer to the object detection task. Then the standard thing to do is to just load it to an object detection model and then tune the detection model. And in such a setting, the different constructions of backbones can actually make a pretty big difference. So here I'm showing a very rough diagram of the three different types of backbones that we provided and highlight their differences in the setting of loading a pre-trained model. First, in the so-called dilated COM5 backbone, the entire pre-trained backbone is loaded and becomes the backbone of the detector. But in the Conv4 model, only part of the pre-trained backbone becomes the backbone of the detector, and that's up until the Conv4 layer. And the rest of the pre-trained model becomes part of the head of the detector. As a result, if we want to study the question of whether a pre-trained model is good for the head, then we might want to use the Conv4 backbone to run our experiments. And this is actually used by the momentum contrast paper because of this. When we look at the FPM backbone, it turns out that this model is different from the other two because it adds some extra layers that needs to be trained from scratch on top of the original backbone. This may cause some other complications. If we, for example, we want to study the question of how well a frozen backbone can perform in object detection, then we might want to consider the other two, which does not need to train new layers from scratch. In fact, this type of research questions about pre-trained features and pre-trained backbones, they frequently arise in the development of MoCo and other representation learning methods. And that's why these different models are still useful for research, because they are sufficiently different, and having these models will provide us with different perspectives when looking at new problems. And let's come back to our model zoo again. And to know how good a model is, we look at the evaluation metrics, and here are the APs. When comparing models against each other, especially in research papers, we need to be very careful about the recipe of training, because a comparison between two models that may appear to be a fair comparison, but they can actually be affected by many other hidden factors, such as how long the model has been trained, the data preprocessing that's used, all kinds of hyperparameters, and the so-called bells and whistles. In Detectron2, because everything in the models will come from the same code base, and we make sure to have this recipe consistent. That's why we list the comparison in the models in this way. We do provide different settings for the length of training, which is the learning rate schedule column in this table. This is because a shorter length of training is cheaper and more suitable for the development of new ideas, while a longer training costs much more, but it will give more stable results. So we provide both. In addition to the so-called recipe, many tiny implementation details can also affect the model. In this figure, we show the AP of the same mass Gaussian model trained with the same setting. We can see that the model gets more accurate in Detectron1 than in the original paper, and it improves further in Detectron2. The underlying reason is that a detection system has many low-level implementation details. Issues like how a resize function is implemented or how to compute the size of a bounding box, they may seem trivial, but they can actually affect the model. When building Detectron2, we took a more systematic way to look at all these issues and try to address them to improve the performance of the model. In addition to accuracy, we certainly also care a lot about the computational cost of the model. One way to measure the computational cost is to use its real-world latency as a metric. However, this metric is unreliable for many different reasons. When comparing the latency of different models, especially in many papers, it's often hard to fully control the environment. But the environment obviously affects the latency a lot. For example, it's hard to let everyone use the same hardware, and especially older papers typically use older hardwares, which put them in a disadvantage in the comparison. The software environment obviously also affects the speed a lot, especially if we take into account the different low-level optimizations that each library may have done. People who are experts in low-level optimizations can easily make the same code run many times faster on the same hardware. In addition to the environment, the details of how the latency is measured can also be a source of difference. One may evaluate the latency in a batch setting, but another may evaluate with single image prediction. And a model may also have certain pre-processing or post-processing specific to the model, and it's hard to actually define how to measure the speed and whether this preprocessing or post-processing should be included or not. All these subtleties can make it quite challenging to compare latency between models. Even in Detectron2, such issue still exists. Even though it's a unified codebase and all models run in the same environment, we can still see some situation where, for example, a model may be faster than another model in one PyTorch version, but it becomes slower in a different PyTorch version. Or it may be faster on GPUs, but slower on CPUs. To see a real example of how problematic these issues can be, especially in research, let's look at a figure from some paper. These types of figures are very common in papers. It plots the speed and accuracy of different models in a graph, and they try to convince readers that the new models has better speed accuracy trade-offs. In this particular figure, the point G is a faster RCN with a ResNet 50 feature pyramid network backbone. However, if we are going to take the same model from Detectron2 today and plot it on this figure, the point G will move to here. The improvements come from better hardware, better software, and also better training recipes that are used in Detectron2. So when we look at figures like this, we really need to be aware that these points can actually shift a lot due to many different details, and the conclusion from such comparison should often be taken with a grain of salt. Here, the shift on the y-axis is due to the different recipes that are used, and the shift on the x-axis is because the inference latency can depend on a specific software and hardware environment, which are hard to control between different publications. If we have a more objective measurement of computation, we won't have to worry much about that shift on the x-axis. So another measurement that people often use is flops. Flops, which stands for the number of floating point operations, and it basically counts roughly how many computation is needed to compute the outputs. It is very commonly used in visual representation learning or image classification. Compared to latency, flop is much better defined, although there are still some small ambiguities here and there in its definition. It's pretty much good enough that anyone can compute a flop number without too much disagreement with each other. It still has a lot of other issues though. One is that flop is often data dependent, especially in object detection where some models are by design use more computation when more objects are detected. This situation is very common for RCN models. For this, we provide a solution in Detectron2 that basically computes the average flops over a dataset. The most annoying problem about flops is perhaps that people find it's not always correlated very well with the actual computation speed, which is eventually what we really care about in the end. So this problem happens quite a lot on GPUs because the speed on GPUs is more likely to be bound by memory access than by the computation itself. Some alternatives to flops have been proposed as well, but it's still left to be seen if there's a better way for us to properly measure the computational cost. So for now, both measurements are still useful, and in Detectron2, we also plan to conduct a more thorough analysis of latency, flops, and other metrics such as number of parameters for all the different models, and perhaps also under different inference settings. So in summary, I talked about a few aspects of our model zoo, and especially about how to properly compare models and how we do them in Detectron2. I hope this can help users use them in research. Last, I would use a few minutes to talk about how Detectron2 is used in Facebook production. In Facebook, many teams have developed AI applications on top of Detectron2. A typical application would include the following steps. First, Detectron2 is connected to Facebook storage infrastructure so it can read the larger scale training data in a secure way. Since the models are usually deployed on CPU servers or mobile devices, the standard academic models are often too expensive, so different teams also developed efficient models that are more friendly to the CPU hardwares where we deploy our models, and we hope to open source these models as well. These models will be trained in our large-scale cluster, and finally, after training, it is serialized to a binary format that can be read from C++. These are some There are some graph optimizations, sometimes quantizations as well, to further improve the speed of these models on different devices. A bit more about the deployment step. Right now, we actually have two approaches to deploy a Detectron2 model. One is to convert the model into a Caffe2 format, and this approach is quite mature, and we have pretty efficient runtime on different devices. This is also open sourced already earlier this year. Another way is to convert the model into a TouchScript format by either tracing or scripting the model. This has been used in a few scenarios inside Facebook, but we still don't have enough resource to support it externally. And this is also a large area that we will work on a lot for the rest of the year. That's all for this talk. Thanks everyone for listening. If you want to learn more about Detectron2, you can find more resources online at these links. Goodbye.